Welcome. Let me now describe the second derivative test in general using the language of matrices. So we assume that we have a function of n variables, and we'll call the variables using subscripts as a standard practice when you have lots of variables. So the variables will be denoted by x1, x2, x3, etc. up to xn. We'll also assume that all the first and second order partial derivatives of f are continuous in some region. As before, the critical points of f are defined to be solutions given by the system we get by setting all the n first order partial derivatives equal to 0. Note that in some sense we are taking all the first order derivatives into account simultaneously. Another way of saying this is that a critical point is where the differential approximation for f is 0. Of course, the differential approximation is 0 if all the coefficients in there are 0. Coefficients are the first order partial derivatives. But instead of saying that you have a system of equations, it sounds like I'm saying one entity, one quantity is 0. Even though the quantity that is 0 is the differential approximation involving new variables as well, rather than just the original variables. The second derivative test, phrased in terms of matrices, will sound more like the one variable test than the test we used, but the language is a little bit complicated because we want a certain particular notion of matrices. So we don't want all the entries are positive or something like that. The concept we need is what's called definiteness. It's somewhat complicated to state, so let me break it down rather than just reading off the notes. We start with an n by n matrix. Let me call that Q. Now if I take any 1 by n row matrix, say V, then VQ is 1 by n times n by n, so it will be 1 by n. V transpose is a column matrix, which is n by 1. VQ is 1 by n, V transpose is n by 1. So VQ times V transpose is 1 by 1. So it has just one number in it. Now if I take any non-zero row matrix V, I calculate VQ, V transpose. If it always comes out to be positive whenever V is non-zero, we will say that Q is positive definite. If it always comes out to be negative whenever V is non-zero, we will say that Q is negative definite. If this matrix sometimes comes out to be positive, sometimes negative, then we will say that it is an indefinite matrix. There's also another concept of semi-definite, where VQ, V transpose sometimes comes out to be positive, sometimes 0, but never negative. Then it's called positive semi-definite. Similarly, it's a negative semi-definite. These are cases where the second derivative test fails, so I won't say anything about them. I can take all the second order partial derivatives of f, arrange them in a matrix. So if you think about it column by column, in the first column, I take all the partial derivatives where I first differentiate with respect to x1, the first variable. In the second column, I take all the partial derivatives where in the first step, I differentiate with respect to x2, the second variable, so on. Or you can think of them as arranged in rows. Ith row consists of all the partial derivatives where I differentiate with respect to xi in the second step. So the ijth entry in the Hessian of f is d squared f over dxi dxj. Of course, the order doesn't matter. The Hessian of a function f with continuous second order partial derivatives is what's called a symmetric matrix. If you switch rows and columns, you get the same matrix, or more formally, its transpose is itself. It turns out to be important for calculational purposes. So now we are ready to state the second derivative test for n variables. Take a critical point of f. Evaluate the Hessian of f at that critical point. If that Hessian is positive definite, then the critical point is a relative minimum. If the Hessian is negative definite, it's a relative maximum. If the Hessian is indefinite, the critical point is a saddle point. The condition of being positive definite or negative definite is an infinitary condition because you have to check every non-zero row matrix. Obviously, that's not possible, but it turns out it is possible to decide this in a finite number of steps. The second derivative test we saw for two variables is a way of doing this for two variables. Trying to extend that to any number of variables is very cumbersome and not really practical, to be honest about it. But it turns out there are other methods which are pretty good, which work well for symmetric matrices, which is all we have. However, it's still a lot of calculation, so it's best done using computers or calculators.